Hello. In this video, we are going to solve the same example than in the previous video. So you need to see the previous video first, but with slightly different conditions. So this is actually the same problem. We have our module in our modern processor that have to detect or determine when the system is busy. But the difference now is that we are asked to do the design using only NAND gates. Okay. The reason is that in fact, in most technologies, complementing gates are easier to design, are cheaper to design, need fewer transistors than non-complementing gates. So actually, in any typical technology, an AND gate will normally be implemented by using a NAND gate followed by an inverter. Okay, so it's better to rightly use directly NAND gates instead of AND, because each time I use an AND gate, I will need to in fact use two gates. The same happened with NOR gates. Okay, so in practice, non-complementing basic AND or OR gate are normally not used. We prefer the complemented versions. But the good news is that when we have a sum of products, you already know that when we have a sum of products, okay, we can do it with a first level of AND gates and a second level of OR gates, but we can find an equivalent expression by double complementing this expression and using the Morgan's theorem. So the same operation I can do by changing all my AND operations by NAND and all the OR operations by NAND as well. So once I have designed a circuit or have calculated the sum of product, I can decide to use AND and OR gates or simply NAND gates for everything. Okay, we don't have to transform every single gate. Just take the whole expression, sum of product, forget they are not AND and OR, and use just NAND gates. And the same happen with the product of sum alternative. Okay, just this product of sums I can rightly implement using NOR operations, or followed by inversion, or followed by inversion, or followed by inversion. There are some particular cases you have to consider, that if I have a literal that goes directly to the output, okay, when I transform to the inverting gate, I have to add an inverter here. Okay, if in doubt, just use the expressions, double complement expression, and obtain the expression with the NAND in this case, and you will see that the literal that was alone here need to be complemented now. But most of the time you don't really need to make the calculation. Just use your sum of product and go directly to a NAND implementation. So having said that, sum of product then is equivalent to an AND or a NAND implementation. Okay, so because the problem says use only NAND gates, to use NAND gates only efficiently, we have to make the equivalent to the AND OR, which is start with the expression as a sum of products. We don't have to try both solutions, sum of products of product of sums, because we are limited by the fact that we have to use only NAND gates. So to do so, I just simply copy the solution we already obtained in the previous example for the sum of product case. Okay, so this is our problem moved into our kernel map, and this is the minimal expression as a sum of product, and I simply implement my circuit from this expression. And as I told you, it's not really necessary to convert it to NAND operations here. I can draw my circuit, but when I would normally put an AND gate, now I will put an NAND gate. And when I will normally put an OR gate to make all the OR operations, I will also put a NAND gate, and that's it. Now, what happened with the complement? I have to complement one variable, and here I have some options, because the problem said use only NAND gates. It depends on how strictly you understand these only NAND gates. Okay, maybe it may be possible that you really only have NAND gates in your underlying technology. Okay, it depends on the environment. No, if we don't really know, because the program doesn't say that. The program may have said NAND gates and inverters. Okay. For example, if we are designing an integrated circuit, in an integrated circuit, for example, an ASIC, we are fully designing the integrated circuit. We can use any gates we want. Okay, we will use NAND gates, maybe because in that technology NAND gates are more simple, are more efficient, are cheaper, whatever. But normally, if you are designing an application specific circuit, then there's no problem to have also inverters available. Okay, in case of doubt, you just ask your boss in your design company, or you ask your instructor in an exam. But normally in a regular integrated circuit design, it's not a problem to use inverter as well. But it may be that you are designing your circuit and you are going to implement your circuit using SSI devices, okay, to mount a prototype in a breadboard or something like that. So you are using circuits like the 7400, which has 4 NAND gates, or any other thing like that. So in that case, it may be good to use just only NAND gates, not so you don't need to use additional integrated circuits. Okay. But it's not that important. Normally, only NAND gates may also include inverters. If the program doesn't say it explicitly, just check. Okay. So I will comment both alternatives in the solution. So first, we'll consider that we can also use inverters. So we just go right and draw the circuit. We need to do 4 terms. So I will draw 4 NAND gates. Instead of N, I directly use NAND gates. The literals are as normal. Okay. So these, for example, this term, I'll start with that term here, will be P1 and P2. We also need P2 inverted, so I will use an inverter this time. Okay, so we have P2 complemented. Now we also need P1 and P3, so I will use P3 here. And I'll take P1 from here, P1, P3. So here I have P1, P2. Here I have P1, P3. The next one I will do P2 complemented P4. So I take the P2 complemented from here, and I have P4 here. and the last term, the remaining term is P2, P3. So I connect here, P2, and I take P3 from here, P3. And all that I sum with another NAND gate. So as you see, I'm not changing my expression, just using gates as if they were the original AND OR. And that will obtain the solution for my circuit. Okay. In case that we want to use a strictly only NAND gates, it's easy to do because I can do an inverter using an equivalent gate using a NAND, maybe by connecting together the inputs. Okay, you say when it's 0, it's 0 and 0, 0 that makes a 0. When it's 1, it will be 1 and 1, that is a 1. Okay, sorry, will be a 1 here, and when it's 1, it will be 1 and 1, the AND is 1 and the AND complemented is 0. Okay, so this is an equivalent inverter. So if we strictly need to use only NAND gates, I will just use a NAND gate here, connected to function as an inverter. And that's it. Thank you.